In this work, we introduce a novel framework for designing fast, predictable braking maneuvers that can be employed for real-time robot control. In this presentation, we firstly introduce the research motivation. Then, we detail the mathematics behind the considered optimization problem and key used formulas. Before presenting our proposed solution. Afterwards, we discuss our experimental settings and the obtained results. Finally, we conclude the presentation by highlighting the key features of different braking methods we explored. This research work is motivated by the safety requirements of modern collaborative robotics, where efficiently addressing the performance and safety trade-offs during operation is crucial. For efficient and safe collaborative operation around humans, the robot must integrate predictable braking strategies that allow estimating the braking time and the distance traveled by its parts while braking. That is, the so-called braking distance. Given the current robot state, the minimum possible braking time can be evaluated by solving a final time-constrained minimization problem as encoded in the shown objective function. Besides the compensated robot dynamics, the constraints to be considered also include the physical constraints on the actuator inputs. And this optimal control problem has to be solved considering the initial and final time boundary conditions on different states and control inputs. Although it generates optimal solutions, numerical optimization methods typically impose high computational demands, and it also requires long time to evaluate. This renders estimating the braking distance online impractical. Instead, we propose an alternative braking framework that allows evaluating the robot braking time and estimating the stopping distance online. The overall architecture of our predictable braking framework is as shown. A core concept of this framework is the modal transformation, which relies on diagonalizing the robot mass matrix by means of the eigenvalue decomposition to transform the system into the modal space defined by the eigenvectors of the mass matrix at the braking instant. We also opted for designing a synchronized braking solution, in which all the robot joints stops at the same time. Even such synchronized braking is not energy optimal, since braking of some joints is delayed for the sake of synchronization. It, however, results in more intuitive stopping behavior for nearby humans. The key steps of our predictable braking framework are the following: decoupling the dynamics and transforming joint velocities at braking instant into the modal space. Then, obtaining the maximal feasible actuator limits for the modal coordinates. Followed by designing the individual, decoupled stopping maneuvers geometrically using Bézier curves under these limits, and finally recoupling and applying them for control in the original input space. We now highlight some concepts employed for designing smooth stopping maneuvers for the individual modal velocities. For designing the braking maneuvers in modal space, a simple idea for stopping an inertial moving object by applying a torque in the opposite direction to its motion is employed. Considering a modal mass mqi moving with a modal velocity q.qi, a momentum is generated due to its movement. To break this mass motion, one needs to bring its velocity to zero as quickly as possible. An intuitive idea to achieve this is by applying a counter torque for enough time. Decoupling the robot dynamics results in coupled control inputs in the modal space, whose limits are to be determined for ensuring feasible solutions in the original physical space. This constraint becomes more obvious by considering the original and transformed input spaces. A simple approach to resolve this issue is scaling the transformed input space until it touches one of the boundaries of the original space. In this case, a conservative transformed space is obtained and it can be employed for the design of the braking maneuvers. This approach is named conservative scaling, and its details are summarized in Algorithm 1 in the paper. Alternatively, one can search for more permissible modal limits by means of optimization, in other words, by optimal scaling. Now, we delve into the details of designing the braking maneuvers themselves. For this, we use a quintic Bézier curve. That ensures the continuity of the braking maneuvers up to the jerk level. An exemplary velocity braking curve that was designed following our approaches is shown next together with the original task profile. The whole predictable braking task boils down to estimating the braking times TB of such modal coordinates, where the final braking time is obtained as that of the slowest descending modal coordinate. To test the proposed concepts, we tried to stop in simulation a Franca Amica Panda robot arm with only 3 joints moving in order to simplify the analysis without compromising the generality. We compared the braking performance of our framework, employing both conservative and optimal scaling for the modal bounds, against the optimal time minimizing solution as obtained via numerical nonlinear optimization. For this, the braking action was triggered at arbitrary instants during the following motion phases: acceleration, cruising, and deceleration. The resulting braking times for various braking solutions under different settings were logged and visualized as shown. It can be observed that our proposed braking maneuvers results in longer stopping times. Besides the suboptimality of the modal input limits obtained via both scaling approaches, this is also due to the time invested in smoothly reversing the motion direction using Bézier curves. Nevertheless, the optimal scaling approach seems promising, and our framework have the additional advantage of allowing online computations. Furthermore, we also evaluated and compared the corresponding stopping distances for all methods as reported in the shown table. Now, we wrap up this presentation by providing the key features of different braking solutions that were employed in our work. We compared the braking time itself, the possibility to evaluate the corresponding stopping distance, the computational load of each braking method in terms of time, where we note that our developed methods allows for online implementations and even real-time control. Indeed, this enables accurate prediction of the robot trajectory during the braking action.